Okay, this is part 2 of the study guide. We got cut off, so I just wanted to show that this previous part was part 1. This next part is going to be part 2. So, know the difference between solubility of solids and gases at different temperatures. We already looked at the solubility of solids, and with solids, the solubility increases with temperature, meaning that hotter fluids can dissolve more. What happens with gases? Well, with gases, it's the exact opposite. So if here's your temperature and here's your solubility actually decreases. So if a fish is swimming upstream and encounters warmer water, there's actually less gas in that water. So it's harder for the gas to stay in the liquid. So it's hard for the gas to stay in the liquid, meaning that it comes out. It's not staying dissolved. The solubility is low. When you decrease the temperatures and get it colder, the gas stays. So for example, if you pull out a cold soda, the gas is going to relatively stay inside of that fluid. When you drink it and put it in your mouth, you increase the temperature. It's hard for the gas to stay in the liquid. You decrease the solubility, it becomes less soluble, and it comes out, meaning that it bubbles on the inside of your mouth. How does pressure affect the solubility? Well, if you put the cap back on a soda, the gases start to build at the top of your plastic container. That starts to increase the pressure. That eventually stops the gases from escaping, meaning the gases are going to then stay in the liquid. Well, if they're staying in the liquid, then we have high solubility. So when you increase the pressure, you increase the solubility, and the gases stay in the soda. Know the seeding process of supersaturated liquids. Well, first, let's take a look at supersaturation. And when we have supersaturated, let's go ahead and draw the graph of temperature and solubility. Having something that's supersaturated is when you're starting off with something that is a precipitate. There's your precipitate. We are above saturation, we are above max, so we have solid. And what we did in the lab is we heated it. So one, you heat it. Then if you cool it without crystallization, ours actually crystallized in the lab, but there are some materials that you can cool without crystallization. Cool without crystallizing. Then you have what's called a supersaturated solution. This is those heat packs that are ready to crystallize when you snap them. That causes the pressure wave to go on the inside. That will cause the crystallization to take place. So what we need is a seed crystal. So currently we're above saturation. So step 3 is we're above saturation. But even though we're above saturation, we're still dissolved. So what you need to do is we need to add what's called a seed crystal. And when you add a seed crystal, we also did this with the fluid material. We had a small beaker with aluminum foil on top and the solid on top of that. We poured the solid into the liquid and it crystallized. So you add a seed crystal, and when you add the seed crystal, this acts as a center point for all the material to crystallize on. We are not going to be doing cloud seeding with silver iodide. You can go to the third page. This is going to be calculating the moles. This is another mathematical problem. Calculate moles, volume, or molarity. No, units of concentration in terms of molarity. So molarity, the formula is equal to moles over liters. Remember, we can create a density triangle for this. Molarity is moles over liters. And so from this we can derive two others. Moles is going to be equal to, if you cover up the moles, you get molarity times liters. If you cover up the liters, liters is equal to moles over molarity. So the units of moles are moles. The units of liters are going to be liters. And the units of molarity, when you have moles over liters, is capital M. So that's one of the mathematical problems. The other one's going to be calculating a percent. Okay? So, for example, if you have 3 grams in 100 milliliters, this is equal to a 3% solution. And if you have 16 grams in 400 milliliters, question is, what's your percentage? Well, you just take the top number, then you divide by the bottom number, and then you multiply by 100%. And on your calculator, you'll get 16 divided by 400 will give you 0.04. You multiply by 100%, this will give you a 4%, and it's going to be called mass over volume. And MV meaning that we dissolved a solid inside of a liquid. This has been removed from the test, so you don't need to know this portion here. So let's go to the collision theory. The collision theory is, if you remember, I had these pieces of clay, and the concept of that is that the particles have to collide in order to react. If they don't collide if you have two separate materials, they're not going to react with each other unless you get them to contact each other. That's the collision theory. So in order to react, particles must hit. Particles must collide to react. However, it's not just enough of a collision, because if you remember, the clay was bouncing off of each other. We actually needed that extra energy to force them together. This is called the activation energy. So your activation energy is going to be the energy needed to combine the particles. It's the energy needed to combine, not just collide, but combine those colliding particles. So the collision, this is when they bounce off of each other. However, if you are adding enough activation energy, then they're going to stick. Don't worry for this about reactants and products. We'll get to that when we get to one of the later concepts. Know how temperature and molarity affect the reaction rates and how it's determined by the collision theory. Okay, so this is the black magic lab that we did. How does temperature and molarity affect the reaction rates? When you increase the temperature, we had warmer temperatures. What happened to the time that it took for that color change? When you increase the temperature, you increase the speed of those particles. Remember the solubility races. This increases the collisions, and it's going to increase the reaction rate. They collided faster, so the reaction took place faster. If you increase the concentration or the molarity, in this case, we're not increasing the speed, but you are increasing the number of particles. Remember, concentration means you have more particles. Dilute means you have less particles. So if you increase the molarity, you're increasing the concentration, you're increasing the number of particles. That will then increase the number of collisions. That will also increase the reaction rate. A catalyst is, if you remember in the last part of the experiment, I came by, added 1 little milliliter, and that really sped up the reaction. So know what a catalyst is? A catalyst, what this does is this speeds up the reaction. And what happens to the activation energy? Well, we described this as a hill in your lecture. And if you can imagine that combining your things, we have to push it up this hill, and then once we reach the top, the reaction will then begin. This is the activation energy that's needed to get something going. For example, adding a match to a piece of charcoal. Once the charcoal is burning, it's going to burn by itself, but you have to add this energy to the charcoal, and then once that takes place, it's then going to burn on its own. Well, let's go ahead and add a catalyst. A catalyst is something that's going to make your activation energy lower. So a catalyst, and what happens when to the activation energy? It decreases the activation energy. Know what a reversible reaction is and how to identify it symbolically? Symbolically, it is going to look something like this. An arrow going forward, an arrow going backward. If you remember, if this arrow is going from left to right, this is the forward reaction. If it's going back, this is going to be the reverse reaction. Know what equilibrium is. Note, equilibrium is not equal amount of reactants and products. If you remember, equilibriums are different for different materials. So the simple definition of equilibrium is balance. This is the ruler. This is when the forward rate, we're talking about forward reactions, the forward rate is going to be equal to the reverse rate. If you remember those spheres or beads, marbles being put into the tablespoon, okay, it could only hold a certain amount, and once I reached the maximum, every one that I put in, one would fall out. I put one in, one would fall out, and that continued. So that's what equilibrium is for a reaction. Know the Le Chatelier principle and what happens when you increase or decrease the concentration of reactants and products. So if you remember, reactants, we're going to call reactants R, and products are going to be P. So let's start out with a situation where we are at equilibrium. So here's our ruler, here's my reactants, and here's my products. If I go from reactants to products, I have a forward reaction. If I go from products to reactants, I have a reverse reaction. What happens when we increase or decrease the concentration of reactants and products? So let's go ahead and increase the concentration of reactants. If I increase my reactants, this is like the bromothymol blue. It's sitting at equilibrium. I am increasing the carbon dioxide into the water. So what happens is I increase the reactants. Which direction does this reaction go? This reaction is then going to go forward. If I increase the products, it's going to cause the reaction to reverse. If I decrease the products, meaning if I take the products out, it wants to get back into balance again, so the reactants become more products to balance those out. And the last one is if I decrease the reactants, that means that there aren't enough of them, so the products fall apart to produce them to go back to equilibrium. On to the last page. How temperature and pressure affect the direction of the reaction. So we had this cobalt chloride, and if you added heat to it, it produced two other substances. So if you can draw this reaction here, B plus C. Doesn't matter what they are. But if I increase the temperature, look at what heat is. Heat here is a reactant. These are both my reactants, these are both my products. So if I increase the temperature, I'm increasing my reactant. If I increase my reactant, which of these scenarios is taking place, that means we've shifted it out of balance. There aren't enough products, so therefore it's going to go forward to produce more products. So this is going to be a forward reaction. And vice versa. If I decrease the temperature, I decrease the reactants. We don't have enough of the reactants, so therefore it's going to be a reverse reaction. Exothermic and endothermic reactions. Remember, exo means exit, therm means heat, okay? This is going to be heat coming out. Things are going to get hotter. Endothermic, N, that means you have to put heat in to the reaction. I just realized I missed something. Here's how temperature affects the reaction. How does pressure, let's put pressure over here. We had a lecture on this, and if you remember, we had these substances inside this container. Okay, so we're just going to abbreviate. Let's say I have 1 mole of something plus 2 moles of something. And it's a reversible reaction with something that ends up with 2 moles. This is the piston that's going to be pushing down. So if I increase the pressure by pushing down, it decreases the volume. It decreases the volume, and this is gas that's on the inside. These materials are gases. Which is going to fit better in that smaller space? 1 plus 2, which is 3, or 2? And the answer is the 2 is going to fit better. So since you have less space available, the reaction is going to go forward, or it's going to favor the products. Okay, back to spontaneous and non-spontaneous reactions. Remember, spontaneous reactions are reactions that do occur. Non-spontaneous reactions, these guys don't occur. Okay, things that have more order and energy versus things that are more disordered and less energy. So let's take a look at sugar, C6H12O6. You're going to be eating the sugar, and what's going to happen is your body is going to then convert that sugar into 6 carbon dioxides and 6 H2Os. These guys are smaller. These guys are simpler. These guys are more complex. So where is the entropy? So this is smaller, this is more simple, this has less structure, has less order. This is very structured over here, it's very complex. So remember, entropy is, another word for entropy is disorder or chaos. Disorder. This has less order or more disorder. So therefore, we have an increase in entropy. with these smaller, less ordered products. Here we have a decrease in entropy. Okay, we have a decrease of disorder. We have a decrease of chaos because it's more complex. So again, know what entropy is. Entropy is this disorder. Difference between solids, liquids, and gases. Okay, solids, if you remember, have a lot of order. Gases are moving around, or liquids are moving around. So here's your solid, liquid, and your gases are the most random. This has the most order, this has the most complexity, this has the most structure. So this is very low entropy. Over here, it's more random. This has the most or increased of entropy. And again, complex versus simple molecules. This is a complex molecule. It's ordered, it's built up. It has very little disorder, low entropy. These are smaller, less ordered, less structure, so they have more entropy. Exothermic reactions and those that increase entropy are spontaneous. So if you remember, we had this little chart here, and if you have an exothermic reaction, that causes the reaction to go forward. If you increase your entropy, meaning your disorder or chaos, that pushes a reaction forward. The opposite of those is going to be an endothermic reaction, which will slow a reaction down, and a decrease of entropy, meaning it's more stable and more structured. If you have both of these, you will not have a reaction. If you have both of these, you will have a reaction. That's it. We'll discuss this on Zoom.